Okay, so let's talk about Semiretti's theorem. And well, ultimately I'm going to talk about Roth's theorem, which is Semiretti's theorem for k equals 3. But so Semiretti's theorem was first proved in 1975. It was a long-standing conjecture, and it states that for all epsilon greater than 0 and sufficiently large n, and for all subsets of the integers from 1 to n that have a density at least epsilon. In other words, the size of A is at least epsilon n. Epsilon is like saying we have chosen at least epsilon fraction of the integers from 1 to n. And the conclusion is that A contains a k-term arithmetic progression, which is something that looks like this. It looks like a number, and then you have, basically k numbers that are equally spaced, like the difference is always d. So you have a plus d, the next one would be a plus 2d, a plus 3d, all the way up to this, so that you have a total of k of them. Of course, if d would be 0, that would be trivial, so assume d is not 0. So, yeah, why is such a thing important or nice or anything like that? I guess I can't tell you why it's important, because I don't really know, but it is nice. Why? Because so we were talking about extremal graph theory, which asks questions such as how many edges can a graph have before the graph is forced to contain a certain substructure? And in our case, we talked about containing certain subgraphs. And like Turan's theorem is asking the question, or, well, answering the question of how many edges can a graph have if it has n vertices and it doesn't contain a clique of size r. And, you could ask the same question about, like, why are we looking for cliques of size r? I don't know, just because it's a nice, simple substructure that we could look for. So what would be the analog if we were talking about sets of integers? If we're talking about sets of integers, we would ask a question such as, how many integers can I choose from 1 to n before I am forced to contain a certain nice substructure? And then this kind of opens up the question of what do we consider a nice substructure of integers? Well, it's really a matter of opinion, but arithmetic progressions are pretty nice. They are well organized. Yeah, I like them. They're not too common. If I choose, if I choose k random integers and n is large, then the probability of choosing a k-term arithmetic progression is small. I don't know. They're just kind of nice. They're visually appealing. The numbers are evenly spaced, and I don't know. They just look nice. So that's what we're going to look for, and that's how this is sort of analogous to the extremal graph theory questions that we were asking. This is like a version of that where we're talking about sets of integers and looking for a nice substructure. Anyway, Roth proved the case for k equals 3, and he proved that a bit earlier in 1953. And Roth won a Fields Medal partially because of this, also because of other stuff, but really it was partially because of this. And we're not going to see Roth's original proof as these things go. Once somebody proves it, everybody tries to prove it if it's something important, and then people come up with many different proofs, and the proof becomes simplified and stuff like that. So we're not going to see Roth's original proof. We're going to see something that is more, I guess I would say it more resembles Semeretti's proof. But it's also a lot easier than Semeretti's proof, because Semeretti had to prove this in general, and we're just doing k equals 3. Anyway, here goes. Suppose we have this set, and it is size at least epsilon n. We are going to make a graph out of it, of course, because graphs are the only tools that we really have to talk about in this class. It's going to be a tripartite graph. I've drawn the 3 parts here. There's V1, V2, and V3. And let's pay attention here. V1 has n elements, A1 through AN. V2 has 2n elements, B1 through B sub 2n. And V3 has 3n elements, C1 through C3n. And how do I determine edges? There's going to be an edge from AI to BJ if J minus I is in my set A, the set A that I've been given. BJCK is going to be an edge, so I have an edge between like one of these and one of these, if the difference K minus J is in A. And finally, I have an edge between 2 of these vertices in V1 and V3, so I would have an edge between AI and CK if K minus I over 2 is in A. So that rule's a bit different. It's like the difference of the 2 subscripts divided by 2. And on these other ones, it's just the difference of the 2 subscripts. Okay, well, whatever. This is just a graph. I'm allowed to define it. So this graph would have a total of 6n vertices, n plus 2n plus 3n. And it has a lot of these sort of easy triangles. What I can do is I can pick any vertex from this set. So I'll pick some a sub I, and then I'll pick a vertex from this set by wait a second. Yeah, so sorry, let me fix this. This should say B sub I plus A in the subscript. Because, yeah, what I meant to do is I meant to pick a B vertex, and I want to make sure that, well, this is, I'm claiming that this is forming a triangle. I'm going to have to fix this one as well, by the way. But I'm making a triangle, so I'll tell you what the 3rd vertex is later, but first of all, let's just check that these are adjacent. A sub I is just any old thing from this set. And here I'm doing B sub I plus A, where little a is an element of the set A. And these would be adjacent because if I do the difference of the subscripts, I just get A, which is an element of A, right? I'm just checking this. The difference of the subscripts is supposed to be in A, and it is. The 3rd vertex I meant to put would be C sub I plus 2A. And let's check that that one is adjacent to both of these. Well, these 2 are adjacent. This is a B vertex and a C vertex. And the way you check that is just by doing the difference of the subscripts again. So if I do this subscript minus this subscript, I just get A, and that's an element of A, so we're good. Now let's check that these 2 are adjacent. Well, to check an A vertex and a C vertex, this is the one with a different rule where you do the difference over 2. And, well, if I do this difference, it's going to be 2A, and I divide by 2, I just get A. So, yeah, they are adjacent. So these 3 vertices are all adjacent to each other. Notice that hidden in here is a little hint to why we chose different sizes of sets. The subscript I can just be anything from 1 to n. I just need to choose any vertex in here. And then little a is a member of big A, so little a is at most n as well. Meaning, so if I'm going to write this down, it needs to make sense, right? If I could be as big as n and a could also be as big as n, then I needed this to make sense in order to have b with a subscript that large. That's why the b's go up to 2n, and similarly, this is why the c's go up to 3n, because this subscript might be as big as 3n. So what I just wrote down does make sense. And, right, so what am I claiming about these triangles? First of all, they exist. Second of all, they're edge disjoint. And so I mean that if I choose any 2 things like this, like I choose a value of I and a value of A. Like, that's really what goes into this. If you tell me I and A, then that determines one of these triangles. And what I'm telling you is, when I claim that they're edge disjoint, is that if you give me a different pair, I and A, that will not share any edges with this. Right, like in order to share an edge, actually, let's check this just a bit. Say we have 2 such triangles, like got this one, and we also have a sub I prime, b sub I prime plus a prime, and c sub I prime plus 2a prime. And I won't do all the cases, but let's just check, you know, what if one of these edges is shared? Meaning, so for example, it could be this edge. So this would equal this. In other words, I equals I prime, and I plus A equals I prime plus A prime. I'm just equating the subscripts here. But then, so this tells me that the I and I prime are the same. And now that I know that I and I prime are the same, then basically I can just cancel I and I prime from here, and that tells me that A and A prime are the same. In other words, this is the exact same pair. This is the exact same triangle. These triangles are completely determined by the value of I and the value of A. And I just told you that they have the same value of I and the same value of A. So similarly, if you pick any of the other edges, like I just checked what happens if this edge matches this edge. You could say, look at the edge from the A vertex to the C vertex and say that that's the same as this. Once again, you'll see that I prime and I are the same, and that A and A prime would be the same. So there's 3 cases to check. I only checked 1, but the other ones are entirely similar. And that's what I'm saying, that when I say that these triangles are edge disjoint. If you choose a different pair, for each pair, I and A, there is a unique such triangle. Okay. So, and the number of such triangles is this, because I have n choices for I, and I have, well, however many choices of A, and the size of A is at least epsilon n. So that's epsilon n squared. And none of these triangles, once again, none of these triangles shares an edge with any other triangle. So what I'm getting at here is this is a graph such that it's hard to kill all the triangles by removing edges. Meaning if I remove a set of edges that isn't large enough, I'm always going to have a triangle remaining. Why is that? Because, well, I have all of these edge disjoint triangles, and they don't share an edge. So if I'm going to remove a set of edges that's going to destroy all of these triangles, there's no way for me to basically kill two triangles by removing one edge. So I have all these triangles. I'm going to have to remove at least one edge from each one. So the number of edges that I have to remove is at least this number of triangles. So yeah, so what I did here is I just gave away a little bit. 50 is a larger number than 36, and 50 is a nice round number. So if I remove less than that, so that's why I changed it to a 50. If I remove less than this number of edges, there would always be a triangle remaining in the graph. And what do we have? What do we know about graphs such that you have to remove a lot of edges to kill all the triangles? We know the triangle removal lemma. This says for all positive alpha, there exists a positive beta such that for n sufficiently large, any graph such that removing less than alpha n squared edges always leaves a triangle, such graphs must have at least beta n cubed triangles. So what we have here is, okay, so a couple of things are going on. First of all, our graph actually has 6n vertices, and the triangle removal lemma is about a graph with n vertices, so I have to sort of translate between n and 6n. By the way, that's why I wrote this. We had epsilon n squared, and I wrote it this way, which probably looks silly, but maybe now you realize why. Because 6n is playing the role of n. So I have a graph with 6n vertices, and so this epsilon over 50 is like alpha in the triangle removal lemma. And the triangle removal lemma says that for all positive alpha, there exists a positive beta, and beta can only depend on alpha, right? You know, if you look at the quantifiers, you know, beta is only appearing after alpha, so beta can depend on alpha but nothing else. And alpha is epsilon over 50. So what do we get? We get a beta. It's greater than 0. Beta depends only on alpha, and alpha is epsilon over 50. So in other words, beta depends only on epsilon. Such that this graph must have at least beta n cubed, except n gets replaced with 6n. But it's beta times that cubed many triangles. And here we're using the assumption, and we're allowed to assume that n is sufficiently large, right? That's in the statement of Semiretti's theorem. So the fact that the triangle removal lemma requires n to be sufficiently large is not a problem. Okay, so where are we now? Well, if n is large enough such that this, which is the this is a lower bound on the number of triangles we have total. And this is the number of triangles that would have a certain form, like this form. Right, because we had this special set of triangles, the triangles that look like this. If this is greater than 0, then there must be a triangle that is not of that form, right? Yeah, I guess I'm making this harder than it really is. Right, this is the total number of triangles. This is the ones that are of that particular form. So if this is positive, then there's a triangle that's not of that form. So what can it look like if it's not of that form? Well, it has to have at least a vaguely similar form. So let me go back to the picture. So how can we have a triangle? This is a tripartite graph, so it has to have a vertex from here, one from here, one from here. So say A sub I is your vertex from here, and so that's just anything. The vertex from here would basically have to be that plus something in A. And let me fix everything here, because I made the same mistake that I did last time. Whoops. Yeah. This should be B sub I plus A. This should be C sub I plus A plus B. Okay, sorry, but let me explain this again. So we have a triangle that is not of the stated form, these special triangles that we were talking about earlier. So how can that look? Once again, I have to choose A sub I as any vertex in here, and then I'm going to have a B vertex, and the difference of the subscripts has to be in A. In other words, whatever the subscript is down here, the difference between this subscript and this subscript has to be an element of A. In other words, the subscript has to be, well, it has to be this subscript plus an element of A. So it has to look like this. It has to be B sub I plus A, where I is the same as this I and A is an element of A. And then what could the C vertex look like? Well, once again, I can just say, in order for these two to be adjacent, the difference between this subscript and this subscript would have to be in A, right? Because again, that's the rule for a B vertex and a C vertex. You just look at the difference of the subscripts, and that has to be in A. So the difference between this subscript and this subscript would have to be in A. In other words, this subscript just has to be the same as this subscript plus something that's in A. In other words, I have my A and my B that are both elements of A. And why must this be in A? Well, it's because this and this also have to be adjacent. And if I do the difference of this subscript and divide by 2, because that's the rule for A vertices and C vertices, that difference has to be in A, that difference over 2, and that's this. And now we're done, because these three elements form an arithmetic progression. Yeah, maybe I should note. A is not equal to B. If A were equal to B, then of course these three numbers would all be the same, and that's not an arithmetic progression that counts. A doesn't equal B, because if A equaled B, then we would be talking about one of the triangles of this form, the special form that we were talking about in the beginning, that were all edge disjoint. And why is this a three-term arithmetic progression? Well, basically, you know, there are different cases according to which one's bigger and smaller, but if A is smaller and B is bigger, then this one's right in the middle, and that makes an arithmetic progression. I guess if we, yeah, maybe I'm being, maybe this is too much, but yeah, let's see. There we go, yeah. So this is like an arithmetic progression that's contained in A, and this one is the same as this one, and this one is the same as B, and so this is like the value of D for your arithmetic progression, just in case you didn't see it. But yeah, so that's it. We proved Roth's theorem.